Exactly. You just live. You just live. Okay. Group 1. All have one valence electron. We know francium's the most active metal in that group. Those are called the alkali metals. Did we write that down yesterday? Yes? No? Maybe? No. Okay, let's get it out so we can write it down. Those are called the alkali metals. Alkaline is plural, alkali is singular. Oh, you know, I have it that we wrote it down. Okay, group 1, alkali metals. Alkaline would just be plural. So alkali metals all have one valence electron. They make the positive one ion. This is another popular test question right here. We don't find these, we don't like walk down the street and go, oh, look, there's some potassium on the ground. It will never, ever, ever happen. Good question. Why? Bananas don't have metallic elemental potassium in them. They have a potassium salt. So yes, they have potassium, but that potassium is reacted with something, so it made a salt. Good time to define a salt. A salt is a compound, and a compound is two or more different elements, and the salt will be made from one of these metals or one of these metals, group 1 or group 2, and one of these non-metals over here. That's what's going to make a salt. A salt will always be a metal and a non-metal. So the salt that we put on our French fries is sodium chloride. That's the sodium, which is an alkali metal, and the chlorine, which is over here in group 17, which is a halogen. That's a salt. There are lots of salts. If in January or February when it's freezing outside and there's ice on your driveway, you have to sprinkle salt on your driveway to melt that ice. Yes, no? Okay. Can you put sodium chloride on your driveway? Yeah, sure you can. But when you go to Agway or Home Depot or Lowe's, oh wait, did I say Home Depot? When you go to Home Depot, also known as Home Depot, they don't sell table salt to sprinkle on your driveway. They sell calcium chloride or magnesium chloride. They sell CaCl2 or MgCl2. There's a reason for that. As we go through this, I'll explain why. They don't sell pretzel salt or French fry salt to put on your driveway. It's just a different kind of salt.
Why is salt so slow?
Okay, so let's say you have a little slug. Here's your slug, right? Okay. And if I sprinkle salt on it, the slug is mostly water and that slimy stuff, right? So if I put salt on that slug, let's say I put some sodium chloride on that slug. Well, the concentration of the salt on the outside here is going to be very high. And the concentration of the salt inside the slug is going to be very low. So there's going to be a lot of water and a little bit of salt in the slug. There's going to be a lot of salt outside. Remember osmosis from living environment? What happens is the water that's inside the slug, there's water in here, and there's a little bit of salt, not a lot, just a little bit. The water that's in here is going to start moving out of the slug to try to dilute the salt that I just sprinkled on the slug. And so what happens is the slug loses its water and it dehydrates and it kills the slug. That's what happens. Now, the more salt you put on it, the faster that's going to happen. Remember you did the thing with the tube and you saw the water go in and out. You saw the iodine change colors. It went from like blue to like clear to blue or something like that. It's the movement of water. Do you remember that? It swelled up. the cell swells if water's going into it, and the cell shrunk if the water's coming out. That's exactly what's happening here. Except for the cell is the slug. Poor slug just got annihilated with some salt on it. Go ahead.
If I just ate regular NH, would I live?
Probably not, because this sodium right here is highly reactive with water. So once that sodium hits the water, it is what we call an exothermic reaction. Exo meaning exiting. Thermic means heat. So lots and lots of heat is going to leave that. It's going to actually go on fire. Okay? So the first thing that's going to happen if you put that sodium in your mouth is it's going to burn the inside of your mouth. Now, once that sodium burns the inside of your mouth and reacts with the water, it forms something called sodium hydroxide, which is a extremely strong base. So now you swallow that sodium hydroxide, and it's going to eat away at the inside of your stomach lining because it's very basic. Sodium hydroxide is the stuff they use to unclog sink drains. It's Drano, basically. So, yeah, you don't want to put this in your mouth. However, when the sodium and the chlorine come together, they make a brand new substance called sodium chloride, and that sodium chloride is actually something that you cannot live without, which is interesting because this is poisonous by itself. Chlorine is poisonous by itself, but together you have something that you can't live without. Pretty cool.
Like, how do they use the poison?
It changes to a totally different substance. So you're actually doing what we call a chemical change. Have you heard about that from middle school? Remember when you talked about physical changes and chemical changes? A physical change would be like scissor, still a scissor. That's a physical change. It changed the shape, changed the whatever. Or if I took a piece of paper, which I don't have one right now, here. Paper. Still paper. Just a little bit of paper, a little bit of paper. This is paper. But if I burned this paper, I'm going to have a pile of ashes. Is that paper anymore? No, it's a brand new substance. That is what happens in a chemical reaction. So there's another example. I'm kind of going down a little bit of a rabbit hole, but it's a good rabbit hole to go down. So hold on. Where's my pen? Come on. Ooh. Got this little dumbbell here. So let's say we have H2O. That little S that's right there, what do you think that S means? Solid. Okay? That means solid. What did you call it? Okay? So what is solid H2O? Ice. So this is basically ice. Okay? And then in chemistry, we kind of write it with, I call these little chemical stories, right? So let's say I have an ice cube on my desk. This is H2O solid. This arrow right here means something magical has happened. Magic happens here. Okay? And then we end up with H2O with a little L after it. What do you think the L means? If this means solid, this means liquid. Good. So that's liquid. Okay? So what happened here? It's a story. Okay? This is nothing more than a story. And you're going to be writing these stories. You started with solid water, magic happened, and you got liquid water. It's still the same water. This is what you had in the beginning of time. This is when something is happening to it, and this is what you have when you're done. Once upon a time, something happens, happily ever after, right? That's kind of the way it works. Did we change the substance that we had? No. We started with water. We ended with water. This is a physical change. This is not chemistry. That's physical. Now, let's take this. Hydrogen with a little G after it. What does the G mean? Gas. Oh, you see how fast you learn? and O2 with a little G after it. Gas. Okay. Think, because I taught you this already, what or why did I put a 2 there? There's 2 hydrogens. Very good. And what do we call it when you have 2 of the same element that are right next to each other like that? There's 7 of them on the periodic table. Oh crap, did I not tell you this? Because you're looking at me like I'm crazy. Diatomic elements. Is that in your notes? Maybe. Better look, because if it's not, we need to do that. Okay. Maybe some of you have it, some of you don't. Let's write it down. There are 7 elements on the periodic table that are what we call diatomic elements. Here they are. Yes, shaped like a 7. So I did say this. Was it in the ed puzzle? All right. Nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. There's 6 of the 7 elements that are diatomic. And what that means is that when you're wandering down the street, if you bump into an oxygen, there will always be 2 oxygen atoms connected to each other. Always. Not when oxygen is in a compound, but when oxygen is oxygen. Okay? There's 6 of them here. The 7th one is this hydrogen way up here. See this one? 7th one. I think that's on your quiz tomorrow, so I'll make sure that you know that. N, O, F, Cl, Br, I, and H are your 7 diatomic elements. Anytime I write those down, I will put a little 2 in the bottom right corner. That little 2 is telling me there are 2 of that atom connected to each other. Got it? Okay. Now, I gotta erase this because I want to go back to my other thing. So here, we've got 2 hydrogens. So really what it looks like is this. HH. It's a diatomic element. This oxygen is also one of the diatomics. I'm going to do it in red, just so that they're different. Now, remember what I said. This is what I have once upon a time. This is the beginning. Then I get an arrow, which is the magic. When I'm done, I end up with H2O. Oh, yeah. What the heck just happened here, folks? Okay. I started with hydrogen gas. I also started with some oxygen gas, but I ended up with something totally different than what I started with. This is a chemical change. Now, somebody is inevitably going to ask me the question. Go ahead, ask it. What happened to the other oxygen? I knew it was coming. And I've told you already, if I start with something, I better end with that. Okay? It's still there. Okay? The reason why I didn't write it in right now is because in order for it to be there, we have to add these numbers in front. These numbers are called coefficients. So in order to make water, I actually have to start with 2 H2s. Now we get to do some real chemistry. And 1 O2. Where's my black? And I will make 2 H2Os. So look what happens here. Everybody's eyes up here after you're done writing that down. I want everybody looking at me because this is where you have to be really tuned in because we're going to start doing some real chemistry stuff here. You see these 2 hydrogens? This is a group of hydrogen and this is a group of hydrogen. This 2 in front, which is called the coefficient, tells me how many groups of that H2 I have. This number tells me how many groups of O2 I have. Okay? When you have that, okay, this is the once upon a time. Now the magic is going to happen. The magic is where all of these things separate. So if I drew a line, now I have this. That's the magic, right? So do you understand that if I have 2 groups of H2, I have really 4 atoms? Do you see those? Okay, there's my 4 atoms. I have 1 group of O2, so I really have this. Okay, see it? Now, remember, this is magic. Well, they don't all go back to looking like this. What happens is they go and they look like this now when they're done. So how many groups of H2O did I make? Remember, this is what I started with. They all break apart into their individual pieces. They finish by looking like that. Once upon a time I had this. Blah, 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 blah. Story, magic happens. The end. Okay? It's a story. When you read a chemical equation, it's literally a story. It's telling you what is happening. Now, back to the physical and chemical change thing. Because I changed what I had in the beginning to something totally different at the end, it is now a chemical change. Here, the water stayed water. Here, the hydrogen and oxygen made something totally brand spanking new. Sometimes that happens, sometimes this happens. Okay? Physical changes don't change what you have. Chemical changes change what you have. Alright, so there's a lot going on here. Let's just reiterate. We had diatomic elements. These always get a 2. They are elements. Elements because there's only one type of atom. This O doesn't get a 2 on it because it's part of a compound. A compound is 2 or more different elements. This is 2 different elements, a hydrogen and an oxygen. So the subscripts, these numbers down here, have different rules when you're doing a compound than when you're doing an element. Elements either get a 1 or a 2. A 1 if they're a monoatomic element, which is most of the elements on the periodic table, or a 2 if they're one of those 7 that I just showed you. These subscripts have rules. I'm not telling you the rules yet because we have to learn how to write our formulas first. Okay? That's why there's not a 2 on here. If I put a 2 on there, it's not water anymore. Does anybody want to take a guess what H2O2 is? It's hydrogen peroxide. It's not water anymore. If I put a 2 there, it would be hydrogen and oxygen made hydrogen peroxide. How'd we go down this rabbit hole? We were talking about slugs. We were talking about physical and chemical changes. That was a cool rabbit hole to go down. Anyway. Alright, so everybody knows the metals, the nonmetals, the metalloids. Group 1 are called the alkali metals. That's where we were. Group 2 are called the alkali earth metals. Sometimes called alkaline earth metals, if it's plural. Oh, I know. I was talking about walking down the street and not finding sodium just hanging around. That's how we went down that. Because these guys are so reactive that they're going to form salts immediately. Because they want to lose that electron very, very quickly. And so, no matter who goes past them, if they encounter oxygen or fluorine or chlorine or bromine, they're going to react very quickly. That's what's happening. The second group, those alkali earth metals, these are also reactive. They're just not as reactive as alkali metals. Okay. Then you asked me about the potassium being in a banana. This potassium that's in the banana, okay, is a potassium salt. It's not pure potassium element. Okay? Your body can break that salt apart and use the potassium, but you're not eating potassium metal. Okay? All right, group 3 through 12. Right here. 3 through 12 are called the transition metals. I wrote on this, so I didn't do this with you guys? This must have... What? You can't see it. You can't see it. Okay? The transition metals, groups 3 through 12, are the metals. They're more stable than groups 1 and 2. They actually can lose electrons from various energy levels. They can lose them from the valence shell. They can also lose electrons from the inner shells. And what that does for them is it makes them special in that when you do that, when they lose their electrons, they can form beautiful colored ions. There's a couple of them you know already. You just don't know you know it. Iron. If you look at an iron nail, it looks like metal, right? But when iron loses those electrons and becomes an iron ion, it's going to form a salt, an iron salt, mostly iron oxide. Iron oxide is also known as rust. What color is rust? Reddish-orange. A nice, beautiful reddish-orange color. It's really not beautiful when it gets all over your clothes, but it's a color, right? Here's another one. Look at copper. Copper. Metallic copper. Shiny. It's not really shiny in my example here, but it's shiny. It's a metal. Okay? What happens when it reacts with oxygen? Turns green, like the Statue of Liberty. Okay? That's because that copper is no longer metallic copper. It is a copper ion salt. This will all make sense as we go through this, right? All right, so these transition metals are colored ions in salts. Popular question that you will be asked. Which of the following is blue? And what you're going to be looking for is something in this area. They're going to give you 4 choices, like aluminum chloride, copper chloride, magnesium chloride, and lithium chloride. So there's your 4 choices. Which one is blue? Does it matter what color they say? Blue, purple, orange? No. What you're looking for is a metal, metals to the left, that is going to be in this section. Is aluminum in that section? No, it's right here. Is copper in that section? Yes. Ding, 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 ding. Is magnesium in that section? No. Is lithium in that section? No. So it doesn't matter what the color they ask you for. They just want to know, do you know that this section is where your colored ions are going to be? My favorite one happens to be this one. Okay? It makes lots and lots of different colors, but one of my favorite colors it makes is a dark, dark purple color. Like a real purple. It's pretty cool. Alright, so that's groups 3 through 12. Form colored ions in solutions. Now let's do group 17. We skip over 13, 14, 15, and 16 because they got funky names like Chalchalcogen. Who the heck cares about those guys? So I will call them the boron group, the carbon group, the nitrogen group, the oxygen group. Just make our lives easier. The Regents Chem doesn't ask us this. Group 17 are called the halogens. They are over here. Okay? They're also called the salt formers because, like I said, they are going to attach themselves to one of these metals that are in group 1 or 2, and they're going to make a salt. Our favorite salt, French fry salt, sodium chloride. You go to the dentist and he puts fluoride on your teeth. He's putting sodium fluoride. It's a salt, but it has fluorine in it. That's the halogens. Okay? And then the last group is group 18, which are called the noble gases. These are all of our gases. They are inert, which means they don't react because they have full valence shells. They have 8 electrons in their outermost ring. So these guys are not going to react at all. Okay. All right. I know on the quiz tomorrow there are the diatomic elements, know them. Metals, nonmetals, and your metalloids. Know your solids, your liquids, your gases. Know the names of your groups: alkali, alkali earth, transition, halogens, and noble gases. Your most reactive metal is going to be down here. Your most reactive nonmetal is going to be up there. I think that's pretty much all we've done so far. Sound good? Valence electrons, you should know that at this point. You should know how to draw a Lewis dot diagram of something. Look at me. If I ask you to draw nitrogen's Lewis dot diagram, how many dots is it going to get? No. Why are you guessing? 5. It has 5 valence electrons, so 5 dots. 1, 2, 3, 4, 5. Don't guess. Look at your tables. If I asked you to draw aluminum's Lewis dot diagram, how many dots does it get? 3. All right, my friends. See you mañana. Yeah?